This is the 5th session in the Sustainable Development course, and in this presentation we will discuss the emergent field of industrial ecology, or, as it is sometimes known, industrial symbiosis. Industrial ecology has its roots in several technical modes of analysis, including material flow analysis, substance flow analysis, and life cycle analysis. The field of industrial ecology has taken hold most strongly in Europe and increasingly in Asia. In addition, virtually all of the technical universities in Europe and Asia have academic programs in industrial ecology. The field has less of a profile in the United States, though there are strong specialist programs at Yale, the University of Michigan, and Carnegie Mellon, among a few other places. The concepts that are part of the field of industrial ecology sit at the heart of a variety of eco-labeling programs in Europe, where the information generated by this array of tools is increasingly being used to measure the ecological impacts of industrial and consumer products, and to make this information available to end users. Let me start this session off with a question. What comes to mind when you think of a metabolic system or a metabolism? I think that the prevailing tendency, not at all inappropriately, is to associate a metabolic system with the functioning of the human body. We take in a variety of daily material inputs, including oxygen, water, and food. These inputs are then subjected to various metabolic processes, and then the resultant waste products, carbon dioxide, urine, heat, are expelled. It is readily possible to appropriate this notion of a metabolic system and apply it at various geographic scales, to a city, a region, or indeed even to a nation. In other words, a city can be construed to function in many respects as a living system, like a body or an ecosystem that takes in certain raw materials, processes these inputs, and generates outputs or waste products. The diagram pictured here is a stylized example of how this process works for Sydney, Australia. Various amounts of energy, water, food, and timber products are drawn into the city so that it is able to carry on with its essential functions. After processing, various wastes are discharged as different waste streams. We can understand these processes in the more formal way displayed in the figure here. The metabolism of a generic city requires food, water, fuel, processed goods, and so forth to reproduce itself on a daily basis. These throughput flows are handled in various ways. Food provides energy for residents, processed goods are converted into finished goods, and building materials are made into houses. It is necessary to introduce here the thermodynamic concept of entropy, with which some students are likely to be familiar, while others may need to harken back to high school classes in chemistry or physics for recollection. The point to be made here is that all linear systems are massively entropic. More specifically, entropy is the normal tendency for a system to go from a state of higher organization to a state of lower organization. The molecular structure of an ice cube, for instance, can be characterized as having minimum entropy, or conversely, maximum order. When the ice cube is exposed to heat and starts to melt, its state of organization becomes more entropic, or it decreases in order. If we scale back up to the level of a city and apply this same idea, we discover that materials with high levels of order or minimum entropy are degraded. They abrade, they burn up, they diminish in quality, they get used up as they move through a city and change into forms with relatively low levels of order, or conversely, relatively high levels of entropy. Let us take a familiar example. A unit of liquid hydrocarbons, oil, when it is pulled out of the ground, has a very organized molecular structure. It has low entropy and high order. The unit of oil is then delivered to a refinery. Process engineers use the term cracking to describe this industrial operation that entails subjecting the oil to high heat, and this treatment breaks the oil down into its constituent parts. The relatively denser constituents are at the bottom of this figure: bitumen, fuel oil, lubricants of various kinds, and diesel fuel. Near the top are the lighter constituents: gasoline, liquid petroleum, gas, and chemical feedstocks. The numbers on the right-hand side of the figure are the relative proportions of each constituent derived from a 42-gallon barrel of petroleum. The point here for our purposes is that refining the oil, the application of intense heat, has increased the level of entropy. The oil has become more entropic. Its order has decreased. You then go to the gas station and fill up the gas tank of your car with one of those constituents, namely gasoline, and burn it in the car's internal combustion engine, a process that entails the application of more heat to break the chemical bonds of the fuel. This increases entropy, reduces order still further. The molecules of oil that you could once hold in your hand are now dispersed into the ambient environment, never to be recovered again. Now, it is important to note that from a chemistry and physics standpoint, it is theoretically possible to recover all of those hydrogen and carbon atoms and reassemble them into a unit of oil. But it would be so costly in terms of energy input and effort that it is not a very practical exercise. Having said this, it is useful as an aside to note that there are schemes currently being considered to capture the carbon dioxide emissions from automobiles as a climate change mitigative effort. When you go to fill up your tank with gas, you would simultaneously offload the contents of an onboard CO2 collection unit into an underground storage tank. Periodically, perhaps once a week, a tanker would come and collect this CO2 from the gas station and take it to a storage facility where it would be geologically sequestered. More detailed consideration of this idea is a topic for another day and need not directly concern us for the time being. Let us turn our attention back to the world of thermodynamics. The concept of entropy reminds us of the law of the conservation of mass. The law of the conservation of mass says that the mass of an isolated system cannot be changed as a result of processes acting inside the system. In perhaps more familiar terms, mass cannot be created or destroyed, although it may be rearranged in space and changed into different types of particles. Just as mass balances are calculated to represent specific chemical reactions, we can construct mass balances of how materials flow through a city. This brings us back to this figure of a decidedly entropy-generating linear system, which serves as a useful depiction of the metabolic workings of a typical city. Again, low entropy, high-order inputs come into the metropolis, and high entropy, low-order outputs leave in the form of various waste byproducts. This system of social organization persists because the cost of raw materials remains relatively low, as does the cost of dispersing wastes to outlying hinterlands. We can also consider alternative, more sustainable models for a city. One option calls for recreating cities as relatively closed-loop systems, or systems with circular metabolisms. Again, for purposes of contrast, a linear metabolism moves throughput through the system in a continuous fashion with high volumes of material inputs and similarly high volumes of waste outputs. A circular metabolism captures and recirculates byproduct flows, and these waste streams become new sources of material inputs. Under such a system of organization, raw material inputs decline because less are necessary to meet the same level of demand, and waste outflows decline because some portion is being recovered and reused. This notion of a circular metabolism has, perhaps surprisingly, taken root most deeply thus far in China, where there is a government commitment to build a so-called circular economy. I encourage you to stop the slide presentation at this point and view the first video clip posted to the website entitled Chinese Circular Economy that provides a futuristic look at plans to put this idea into practice in a new city being built near Shanghai. Let us now move from a discussion of urban metabolism to a related set of ideas on which the field of industrial ecology is built. We tend to interpret environmental risks in terms of overt pollution generated by industrial sources and have developed elaborate regulatory systems to limit the adverse risks to which we are exposed. Indeed, in terms of the sequential stages that comprise the progression pictured here, we remain, particularly in the United States, largely focused on regulation and modest levels of materials recycling. This situation puts us at a rudimentary level of policy evolution. We have really yet to move to the creation of comprehensive recycling systems, and we have yet to integrate any real sense of environmental responsibility into corporate operations. We thus have a long way to go before we get to a stage where we can confidently claim to have achieved what we will refer to in this session as a full industrial ecology. This approach is terribly inadequate and honestly quite primitive in a strategic sense, and does not begin to help us move in the direction of more sustainable modes of production and consumption. We can apply to industrial processes some of the same metabolic concepts that we previously discussed with respect to cities and regions. The analog to a linear urban metabolism for an industrial firm or sector is known as a Type 1 industrial ecology. In the case of a Type 1 industrial ecology, there are no limits on raw material inputs. Throughput is processed in various ways, and then the wastes are discharged. The throughput flow is linear from raw materials to processed goods to waste byproducts. And this is a fairly accurate characterization of how we run our industrial systems today, with a couple of key exceptions, like the flow of copper, for which we have developed fairly comprehensive systems for recovery and reuse. The aim, though, is to move from a Type 1 to a Type 2 industrial ecology. A Type 2 industrial ecology is characterized by more limited material inputs because a sizable fraction of throughput flows is recovered through the recycling of wastes. Accordingly, aggregate waste flows are reduced because byproducts are rechanneled back into useful productive activities. In a Type 3 industrial ecology, all material loops have been closed. No new raw material inputs are required, and solar energy is the only input into the system. Waste flows out of the system have been entirely curtailed with the advent of comprehensive recovery and recycling of waste, and the use of these recovered materials in lieu of new raw materials. The whole notion of waste has been eliminated. With this as background, we can define industrial ecology in the following terms. Industrial ecology is the means by which humanity can deliberately and rationally approach and maintain a desirable carrying capacity, given continued economic, cultural, and technological evolution. The concept requires that an industrial system be viewed not in isolation from its surrounding systems, but in concert with them. It is a systems view in which one seeks to optimize the total material cycle from virgin material to finished material to component to product to obsolete product and to ultimate disposal. Factors to be optimized include resources, energy, and capital. Let us take a break here to view two further video clips. The first one features a short series of comments by Daniel Goleman, the author of the recently published book Ecological Intelligence. You can also download from the course website a video produced by the Industrial Ecology program in the Netherlands that is jointly delivered by the Technological University of Delft and Leiden University. When we return, we will consider one of the most widely discussed examples of industrial ecology in practice. One of the most interesting real-world examples of a relatively closed-loop industrial system occurs in the Danish city of Kalundborg. The figure here is a schematic diagram of the major components of the industrial district in Kalundborg. Sitting at the center of this eco-industrial assemblage is a coal-fired electric utility plant and an oil refinery operated by Statoil, the large Norwegian oil company with operations in Denmark. The power plant and the refinery trade wastes. The power plant sends waste steam that otherwise would have been vented to the environment to the refinery, and the refinery in return sends cooling water and fuel gas to the power plant. Steam from the power plant is also used to provide power to a pharmaceutical facility operated by Novo Nordisk. Waste heat from these industrial facilities is distributed to a network of local greenhouses and to provide district heating. In Scandinavia, it is uncommon for individual residences to have their own means of heating hot water. Instead, it is distributed from a central neighborhood boiler. The sludge byproduct from the scrubber at the power plant, which is calcium sulfate, is used as an input at a local facility that manufactures drywall. Heat from the power plant is also used to heat local fish farms, and the fly ash is used in the mix to make cement and road paving aggregate. Moving to the left side of the figure, we have sludge from the pharmaceutical plant being used as fertilizer by local farmers, and sulfur byproduct from the refinery being sent over to a plant that manufactures sulfuric acid. We have in this eco-industrial park a complex series of waste exchanges occurring, where byproducts cascade from one industrial facility to another rather than being disposed into the environment. In the language of industrial ecology, the waste of one industrial process becomes a feedstock for a subsequent process. One of the most important tools of industrial ecology is called life cycle analysis, or life cycle assessment. I am not going to have the time here today to provide more than the barest introduction to the topic. LCA is a very engineering-intensive tool, and detailed discussion moves very quickly into technical areas that are beyond the scope of this course. I will, however, point out some resources that would be useful to anyone with an interest in the detailed specifics. LCA is an engineering accounting procedure to assess the full range of environmental impacts across the entire lifespan of a product. Like a customary accountant, working industry keeps track of the financial dimensions of the various stages of product assembly and distribution, a life cycle analyst measures all of the environmental dimensions across the entire process of product assembly, use, and eventual disposal. We first need to recognize that products give rise to adverse environmental effects from the point at which the raw materials are acquired. In some instances, this could be a mine site where the elemental inputs of certain components are extracted. Overburden needs to be moved, and in certain cases harmful chemicals are applied to separate the constituent parts of the mined material. Frequently it is necessary to apply large amounts of energy and to release sizable quantities of carbon dioxide to carry out these tasks. The mined materials need to be transported to a processing facility, an activity that again requires the application of energy and results in the emission of further amounts of carbon dioxide. These materials are then transported somewhere else and subjected to a manufacturing operation where they are combined with other materials that have arrived from other distant locations. Again, another round of environmental impacts is generated in the form of energy inputs and waste outputs. More transportation is then required to move the finished goods through final distribution channels. All of this activity takes place as it were, backstage and in advance of any point of contact between the goods themselves and end users. The goods are then brought home and consumed in various ways. In many cases, say in terms of the relatively simple instance of bottled water, consumption is a fleeting activity, and the waste of the product, or the product itself, is discarded for final disposal. Measured in material terms, some 80% of consumer goods are discarded in less than a couple of weeks, some in just a matter of moments. Life cycle analysis seeks to account for the range of environmental effects that occur at each phase of this often lengthy process, and to produce a final metric that enables analysts, and increasingly final consumers, to measure the cumulative impacts of particular products, from a simple product like a container of yogurt to a much more complex product like a photocopier. An expertly prepared LCA oftentimes leads, from the standpoint of the end-use consumer, to surprising and counterintuitive results, because so much of the environmental burden, what is sometimes referred to as a product's ecological backpack or ecological rucksack, is not readily apparent to people sitting at the downstream end of the production and distribution system. For most consumers, all that is seen is what takes place during the use phase, and we, perhaps understandably, inflate in our minds the relative importance of the use phase relative to everything else that is involved with the production and distribution of products, because so much of this activity takes place out of sight. It is also important not to underestimate the role of transportation. In a global economy characterized by vast international supply chains, a key element of contemporary unsustainability is attributable to the large amount of energy required to move raw materials, unfinished goods, fabricated materials, and subassemblies from one manufacturing site to another. The figure here provides some insight into the global reach of Dell's supply chain, where some computer components are manufactured in Japan, Taiwan, Singapore, others come from Mexico, China, and France. The rationale for this fragmentation is to take advantage of lower labor costs in some parts of the world. But the other side of a quest for ever lower costs is that environmental impacts accrue across the full length of the supply chain. Let us take a very simple example of how we might apply LCA in practice. There has over the years been untold anguish over which diaper alternative is more environmentally sound, disposable or cloth. The controversy has probably been blown out of proportion owing to the fact that new parents tend to experience a burst of environmental consciousness, and this issue becomes the battleground on which they make their stand. Regardless of the specific motivations, the decision concerning which option one might opt for on the basis of an LCA provides a good opportunity to demonstrate the utility of this technique. For the sake of the example, let us make the decision a bit more complicated. Instead of two options, disposable versus cloth, let us put three options forward. Disposable, cloth diapers that are laundered at home, and cloth diapers that are picked up and delivered by a commercial laundry. On the basis of your own impressions and your own sense of ecological awareness, which alternative do you think affords the best choice? To answer this question analytically, the first thing we need to do is to distinguish among the three categories of environmental effect. First, there is feedstock and process energy, mostly to produce the plastic and absorbent material in the disposable diaper. Second, there is the energy for washing. In the case of the two cloth alternatives, we have energy to operate a home washing machine and dryer, and for the laundry service, there is energy to run the commercial scale laundering equipment. Finally, we have a miscellaneous energy category, mostly comprised of energy for delivery and transportation. What this simple LCA discloses is that the disposable alternative is problematic, not surprisingly, from the standpoint of feedstock and process energy for the manufacturing process, and requires a relatively small amount of energy for transportation, mostly to deliver the diapers to retail outlets and to bring shoppers to the supermarket. The cloth diaper laundered at home is low on feedstock and process energy, as we would likely expect, but it does not score so well on washing energy because of all of the hot water that needs to be heated for laundering. Finally, the commercially laundered cloth diaper requires less washing energy than the home laundered alternative because the commercial washing equipment runs at higher efficiency than an ordinary household washing machine. We do also in this case need to account for the energy required to operate the delivery and pickup vehicle. It is, though, important to realize that we could have used another environmental metric for this LCA, and the result may have turned out somewhat differently. At the same time, the LCA could have aggregated across a whole host of impact categories: energy, greenhouse gas emissions, toxic materials, space in a local landfill. This more complete kind of analysis runs into problems because there is no clear-cut way to equate and sum across impact categories. How do we, for instance, compare asthma risks with sea level rise risks? What one discovers on the basis of this simple LCA is that from an energy input perspective, the much maligned disposable diaper actually comes out as the superior alternative. Before we move on, let me just highlight one other complicating factor. We did not previously consider how the energy to heat the hot water for the washing process was generated. On one hand, if we lived in a part of the country that was heavily reliant on coal, and our principal concern was greenhouse gas emissions, the cloth alternative would have been judged to be more environmentally problematic because of the relatively large CO2 emissions associated with the generation of coal-powered electricity. On the other hand, if we lived in a locale that derived its electricity from wind, solar PV, and geothermal, the environmental dimensions of hot water heating would be much less consequential. This simple example, though, should give some idea of how quickly LCA can lead to some very complex methodological and technical issues. We can derive a better appreciation of the complexity associated with LCA if we apply these ideas to a more elaborate product, like an automobile. For the sake of the example, let us contrast two Toyota models, a hybrid Prius and a Yaris with an internal combustion engine. Both vehicles are roughly the same size. For the sake of argument, let us presume that the only difference is in their power system. Just from a conceptual standpoint, it is instructive to think about the impact categories that are likely to be most relevant: environmental impacts of materials manufacture, the environmental impacts of vehicle assembly, the environmental impacts of vehicle use, which is the category that we are most liable to think about, and we cannot forget about the environmental impacts of end-of-use disposal. When we add up each of these sub-LCAs, we will have a figure that, if we have done a thorough and comprehensive job, give us a good approximation of the total life cycle impacts of each of the two Toyota models that we can then use for comparative purposes. In this case, the following impact categories are identified: material production, vehicle production, driving, maintenance, and disposal. To start, we can evaluate the two vehicles on the basis of carbon dioxide emissions. In both instances, the volume of CO2 emitted during the production phase pales by comparison to the releases incurred during the use phase. Maintenance and disposal make relatively minor contributions to the overall total. In terms of this metric, the Prius would appear to be the most desirable alternative because its electric motor allows for a reduction in CO2 emissions over its internal combustion counterpart. However, if we are more interested in nitrous oxide emissions, the two vehicles finish up in more or less a dead heat, though there are some differences across the various stages of the car's assembly and use. The same holds true for sulfur oxides, for particulate matter, PM, and for hydrocarbon emissions. What is perhaps interesting from this example is that it is only on the basis of CO2 emissions that the Prius scores a clear advantage. One would not necessarily know this from Toyota's marketing material about the Prius. At least until recently, the company had successfully managed to wrap the vehicle in a bright green aura, despite the fact that its environmental advantages are, all things considered, relatively limited. Let us take a break for a few minutes to view two more video clips. The first is an excerpt by Tim Grant, co-author of a primary textbook on the technical dimensions of life cycle analysis. The second is a more entertaining treatment called The Story of Stuff that has received a great deal of acclaim in the 2 or 3 years since it was released. The film has emerged entirely unexpectedly as a popular teaching tool for communicating the essence of life cycle analysis, as well as for enlightening people to the largely hidden impacts of contemporary lifestyles. It runs for approximately 20 minutes. Both video clips can be downloaded from the course website. Let me say a final word here about LCA. If you're interested in the technical dimensions of LCA, a useful instructional program is available through a series of free distance learning modules produced by the Harvard School of Public Health and the École Polytechnique in Lausanne, Switzerland. It is accessible at the website listed below. In addition, Professor Reggie Caudel in the Department of Industrial and Mechanical Engineering at NJIT teaches a course on LCA that provides training in some of the main software tools for preparing life cycle analyses. Before concluding this session, let me identify 6 key principles of industrial ecology. First, products, processes, services, and operations can produce residuals, but not waste. In other words, waste becomes an outmoded concept. There is no such thing as waste in industrial ecology. After all, where is the waste in a well-functioning ecological system? All ostensible waste products become feedstocks for subsequent processes. In an industrial ecology, production-consumption loops are closed, and no materials are leaked out of the system. We will turn back to this idea in the next section in the context of the work of Bill McDonough and Michael Braungart. Second, every molecule that enters a specific manufacturing process should leave that process as part of a sellable product. In this sense, industrial ecology is inherently pragmatic from a cost accounting perspective. Is it not a little irrational for firms to spend money on material inputs that do not find their way into saleable products? Moreover, the observation is made that it is more than a little bit ludicrous to spend money to purchase feedstocks and then to pay again to have someone safely dispose of them as hazardous waste. Third, materials used should be the least toxic for the purpose, all else equal. There are vast numbers of chemicals, many of them used in surprisingly large volumes, that have never been tested for their carcinogenicity, mutagenicity, or teratogenicity, and we know even less about their synergistic effects. These untested chemicals find their way into products all the time. Sometimes we learn after the fact about their harmful effects on human health and ecological systems. But they are used, and they continue to be used, because they are cheap to produce. Fourth, industries should get most of their needed materials through recycling streams rather than through raw materials extraction. As we have seen in previous sessions, this means of procurement does not occur on a widespread and consistent basis today. It is oftentimes cheaper to procure raw materials and ship them over long distances than it is to rely on recycled waste streams. Even at the household level, there is a pronounced stigma associated with second-hand goods. Fifth, every process and product should be designed to preserve the embedded utility of the materials used. The emphasis should be based on extended life products and modular design. If anything, the opposite tends to be true today. Rather than designing products on the basis of extended life and modularity, there are economic incentives that actively encourage producers to turn goods over quickly and to encourage premature obsolescence. All products should be designed so that they can be used to create other useful products at the end of their current lives rather than simply being downcycled, as in the case of a plastic bottle that becomes a park bench that eventually finds its way to a landfill. We will talk more about this point in the next section, but there frequently is a tragic failure to consider how materials will be disassembled and reused once the initial product reaches the end of its useful life. As Annie Leonard said in The Story of Stuff, most products are designed for the dump. I would like to finish this session by asking you to review two final video clips. The first features Janine Benyus, who popularized the term biomimicry and has been a stalwart champion of this innovative idea for the last 10 years. Biomimicry takes the industrial ecology metaphor a step further and asserts that we should exploit the design knowledge that resides in nature. Natural selection provides a powerful means for demonstrating superior designs, from the hardness of abalone shells to the strength and endurance of some insects. Benyus is a powerful advocate for the notion that industrial manufacturers should look to embrace the natural environment as a partner and to learn how to model their products and processes on ecologically benign exemplars in nature. The Benyus video clip is approximately 20 minutes in length and is accessible on the course website. Ray Anderson, who founded the floor covering company Interface more than 20 years ago, is another tireless sustainability champion of a somewhat different type. Interface pioneered the idea of selling floor covering in square pieces rather than on those large rolls. The novelty of this concept is that carpeting does not generally wear out evenly. So instead of having to replace the carpeting in an entire room when only a small section is worn, it is possible to exchange a handful of individual tiles while leaving the rest of the floor covering in place. Anderson also developed the idea of renting the tiles rather than selling them. He developed a new market niche around the principle of leasing floor covering services rather than selling carpeting to its customers. The reading by Peter Senge discusses a similar strategy used by the elevator company Schindler. This idea of servicization creates an ongoing relationship between a producer and its consumers that is durable over time rather than the customary fleeting relationship that exists when most people buy a good like carpeting. Under such circumstances, the commercial relationship is a single transaction and does not lend itself normally to an ongoing collaboration. Today, virtually all of Interface's carpet tiles are made from recycled polymeric materials and are themselves fully recyclable at the end of their useful lives. Finally, the practical application of LCA is in evidence in two articles. One, a new scheme in Sweden, in which virtually every food product sold in the country now carries a packaging label that indicates the amount of CO2 associated with its production and distribution. The second example is about a new iPhone application that puts LCA information directly into consumers' hands. Once you finish viewing these two video segments and reading the two articles, you will have completed this session. We will reconvene in the next presentation to consider the efforts of Bill McDonough and Michael Braungart, two other important and prominent figures working on the business side of sustainability, in their case from the standpoint of ecological design.